Welcome to experiment number 8 on the common emitter amplifier. What we're going to be doing today is building and testing a common emitter amplifier for all of the parameters that we discussed in lecture. So this is your starting circuit over here. We've got our AC signal source, RS. The reason we have RS here is a 1K, so that if you have a different signal generator and the internal resistance here is 50 versus 75 ohms, it won't make any difference relative to the 1K. So this is just kind of a token resistor here that we can ignore the internal resistance of the signal generator, whichever one you end up using. Okay, so because our transistors are all coming out with slightly different betas, we can't really do a fixed value for R1 and R2. So we're going to make R2 variable, and then we're just going to adjust R2 to get an ICQ of 1 milliamp. So what we'll do is when we're building the circuit, we will put a voltmeter right here. 1 milliamp through a 1K resistor gives us 1 volt. We're going to set R2 until this reads 1 volt. And then we're going to measure the VBQ, which is hopefully 1.7. And then VCQ, which is hopefully 20 minus 1 milliamp times 10K. Hopefully this will be sitting at 10 volts. And then once we do that, we're going to go ahead with our AC measurement. So we're going to measure dynamic range. We're going to turn up VS until we start to see distortion on V out. As soon as we get the first sign of clipping, we're going to hit our limit for what's called symmetrical dynamic range. But then we'll continue to turn VS up and get the total peak-to-peak dynamic range. So we'll have 2 different values for dynamic range. For power dissipation, we shouldn't have to worry too much about that. 20 volts times 1 milliamp here is 20 milliwatts of power. And that's not really going to be an issue for this amplifier. And then we're going to be measuring the gain itself, V out over V in. V in is right here, and we're going to be measuring that both with the bypass capacitor in place and without. Then we're going to be measuring the input impedance. We're going to replace RS here with a potentiometer, and we're going to zero the potentiometer and set the output voltage to a specific level, a nice round even number. Then we're going to raise the potentiometer until V out, we notice, gets cut in half. When that happens, the resistance across the potentiometer equals the resistance going into the amplifier, and measuring the pot will tell us the R in. We're going to do the same thing with R out. We're going to unplug the load resistor, set the output voltage to a convenient, nice even number like 8 volts peak to peak, and then we're going to install a potentiometer over here and adjust the potentiometer until the output voltage is cut in half also. And at that point, this resistor here will equal the output resistance of the amplifier as well. One additional comment I'd like to make is that when you're presenting your data from this lab, only 1 or 2 students have been doing this, but I'd like you to present your data from now on as a table. So what we're going to have is a table. Okay, and on the left-hand axis, we're going to have theoretical and measured. In some labs, we could have a third category, simulated. And then on top, we're going to have our parameters. So here we're going to have VE, VB, VC, dynamic range, voltage gain with CE, R in, R out. So this is the best way to present your data. You will have additional columns for R in with bypass, R out with bypass, but you're going to have just this large table here with all the numbers right there in front of you. For the rest of your life, this will be a much better way to look at data when you can do a side-by-side comparison, as opposed to having to pick it out of a text in a paragraph, which nobody's going to want to do. When you're out on the job, this is how you present data. Okay, so from your lab reports from now on, for your results section, I just want to see a table, no text, just a table. The text, your description, your analysis, your insights from the data, those would all go in your discussion. Okay, so what I'm hoping to see is this. You'll also notice that this is going to save you a lot of space. So those of you who are going for the 1-page limit, this will actually be helpful to you as well. So this is how I'd like you to present in your results section. Something that looks like this. If you do not get this to fit on the width of a page, you can always break it up. DC parameters, AC parameters presented in two smaller tables. How you arrange them is just a matter of your own personal style. So these are the procedures we're going to follow. We're just going to run through this lab. The 2222A is a very forgiving transistor. It's not likely we're going to fry one. However, if we do want to test it before we do, we can throw it on the curve tracer. If we've got over here, if it'll show up. And let me switch this so that it doesn't give people seizures. Good? Okay. Okay, so this is a transistor we put onto the curve tracer, and we see that it has a beautiful set of curves. It works very, very nicely. So this is our lucky transistor. This is the one we're going to be using for today's experiment. Okay. Okay, very good. So we're here to get started. We have for equipment, we have a Keysight 33500B series waveform generator, ID number 793. We have a Keithley 2000 multimeter, number 383. We have an Agilent dual DC power supply, number EE310A, number 688. We have a Tektronix MSO 2012 oscilloscope, number 635. Okay, and at this point, I'm just going to turn things on and let them warm up. So let's turn on the scope, signal generator. We're using the Keithley this time as a voltmeter instead of an ammeter, and we're only using 1/2 of the DC supply this time. And it's set for 12 volts on V1. We're going to be using V1, but we're going to set this for 20 volts. Using a 20 volt supply. Okay, and we can go ahead with the wiring. We are using a standard breadboard number 05, which has always been lucky for us. So let's start by plugging in our transistor, and I'm plugging it side to side. It'll go emitter, base, collector. Let's move it up so I can attach wires to the bottom as well as to the top. So let's start with the emitter. From the emitter, we have a 1K resistor going to ground. So 1K resistor is brown, black, red. So we're going to plug in that resistor here, going to the ground bus. The ground bus is the lower of the two buses. Okay. And then on the base side, we have two things, actually three things connected. We're going to have our R2, which is this 50K potentiometer. And this one, luckily, only has one lead broken off, which is actually good for us because we only need two leads anyway. I'm going to center the pot before I plug it in. And that's going to go from base to ground. We're going to set this pot once at the very beginning, and then we're not going to touch it again for the rest of the period. Okay. So, and then from the base going high, we have a 100K resistor that's brown, black, yellow. This guy right here. So from base to VDD, VCC, we're going to plug that in there. Okay. And now we're also going to have, going to the base, we're going to have Vin. So we're going to have our input capacitor C1. Now I'm switching to a 10 microfarad capacitor because I saw some bandwidth issues with the 1 microfarad capacitors. So I got 10 microfarad capacitors. These capacitors are electrolytic, which means that they have a plus and minus side. They are polarized. So I'm going to plug in the plus side pointing toward the base because that has the higher DC voltage, like so. And then from there, we're going to go through our S, which is a 1K resistor, which is this guy right here, going off to the side. And that is where we're going to connect our signal generator. So we have our coaxial cable with the alligator clips. The red is going to connect to the input side of RS. The black is going to connect to ground, which I'll put in a minute. Let's put in a ground lead now. And this gives us something that we can clip onto over here. Okay, and then we can plug this into the signal generator itself. The output is turned off, and so it's relatively safe. Let's see if I can tuck this wire in a little bit more auspicious location. Like so. Okay. And then that completes the input side. So all that's left now is the output side. We're going to have RC, which is a 10K resistor, going from collector to VCC. So there's VCC and the collector right there. Okay. And then we're going to have another capacitor that's going to be on our output side. This is going to be our C2. And the plus side of this capacitor is also facing the collector because that has a higher voltage than the output. The output has 0 volts DC. The collector is going to have about 10 volts DC. So we're going to plug that in over there. And then finally RL, our load resistor, brown, black, orange, is a 10K. And that is going to be connecting from the output node to ground. We're plugging that in right here, like so. All right, so now we can connect up our instruments. We have a ground lead here. We're going to connect, oh, I think we've already got one connected. We can connect that to there. Okay, and then our voltmeter is also going to be measuring everything with respect to ground. So let's connect the negative side of our voltmeter to that same ground point over here. And then our positive of voltmeter, we're going to use a probe because we're just taking momentary measurements. So we're going to put this on the plus input up there, like so. And then all that's left is our scope. So we have our 2 scope probes back here. Okay, oh yeah, somebody was being helpful in cleaning up. So the yellow one is channel 1. Let's just see where those unfurl. Okay, channel 1. And channel 1 is going to be connecting to the input voltage, which is the right-hand side of RS over there. Okay, and then channel 2 is going to be connecting to our load resistor. Whoops. Channel 2 is going to be connecting to our load resistor. That's the blue one. And a load resistor is over here. And one of these probes has to be grounded. So let's do this one because it's close to a ground point right there. And at that point, our circuit looks like it should be good. So the next thing to do is let's get our input voltage. We still need to do supply voltage. Let's set the input voltage up first. Okay, so we have a sine wave. We have 1 kilohertz, 100 millivolts peak to peak. Let's see if we can get that to show up on the output side. So let's see which button turns it on.
Channel.
Channel, okay, channel turns it on.
And then bottom left corner.
Okay, there we go. All right, so here on channel 1 of our oscilloscope, we have our wave. It's not holding particularly steady, but that's okay because channel 2 is going to be much bigger. And it's 100 millivolts now. Let's make it bigger than that. So let's go to amplitude, parameters, amplitude, and let's just turn it up, make it a little bit bigger. Looks a little better. Now, if we want that to hold still, we can use the triggering menu to tell it to look at channel 1. And it'll actually hold still and not give us a headache. So this channel 1, we have a nice sine wave. It's about 1 kilohertz. And it's about half a volt peak to peak. Okay. So now we can, this is all set. Let's go ahead and build our circuit. Give it one more looking over. Make sure that everything is okay on the construction. And we just need to connect one more hot lead going from the plus 20 to the circuit itself. And if we played our cards right, we should see a big old inverted wave on channel 2. Okay, we get a big old wave, a little piece of it's inverted, and the reason we're not getting the whole thing is because R2 is not set properly. So now we're going to set R2, try to get the entire wave to show up, like so. And we have an inverting signal. Okay, so remember, this is unbypassed. We're not going to be getting a whole lot of gain out of this. But for now, we just have a proof of concept that everything is working. So now we're going to fine tune R2. We want to see 1 volt on the emitter. So the emitter is right here. We're pretty close, 1.03 volts. Let's see if we can get exactly down to 1 volt. .99, that's close enough. So if we're recording data, your VEQ is 0.992 about, and the theoretical is 1. On the base, we're expecting 1.7, we got 1.61 VBQ, and on the collector, we're expecting about 10, we have 10.2. So we hit the target pretty well for our DC bias point. And as you all know my philosophy on amplifiers, if the DC bias point is correct, you have a good foundation for your circuit, the AC will naturally follow. So let's start with our gain measurement. Our gain measurement, we have the input voltage here and the output voltage there. Let's be clever and measure that with a meter to get some precision. So on the input we have 0.231. And on the output, we have 1.108.
Is that going to be RMS?
I believe that they're both RMS, and as long as they're both in the same units, the gain will be valid. So, but I don't know if this is set up for RMS or peak. I'm not sure how to set that up. But as long as we're consistent, we use the same for both, the measurement will be correct. Okay. So now let's check the dynamic range. We're going to crank up the input amplitude, and we're going to watch for the output here to start to clip. Right now the output is only 1 volt per division, and so that's about 1, 2, 3 volts peak to peak. We can expect the output to get significantly bigger than that. So let's start to crank up the amplitude and look for the first sign of clipping. And we can again use the meter to measure that, so we can make a note of when it clips. But this is where we do have to worry about, is this going to be RMS or peak to peak. It still looks pretty good. I still don't see any clipping. A better way to look for distortion is to switch to a triangle wave, so why don't we do that? So let's do parameters, let's see, waveforms. Let's put it to triangle. Okay, and now we want symmetry. So symmetry, we want a triangle wave, not a sawtooth. That looks like 50%. And that looks very nice and linear to me. It looks like we have a very nice high quality signal. Okay, and so now we can continue to crank it up. We're going to go back to parameters, amplitude, and continue to crank it up until we see any sign of clipping.
Changing it by 0.01 volt peak to peak.
All right, let's make bigger jumps than that. So we're going to go, let's go this way. All right, notice we're starting to see a little bit of clipping on the very top now. Okay, so now we'll do a finer adjustment. And I know this is kind of subjective, but do you all see the little rounding going on right there? That would not show up with a sine wave, but it does show up with a triangle. Let's magnify it. You can see we're starting to get just a little bit of rounding up at that top corner. So that voltage now is 2 volts per division. Let's see if we can get the scope to agree with the dial. So that's counting divisions. That's 2, 4, 6, 8. We're about 10 volts peak to peak on this wave. And the meter is reading 2.9 volts. So it looks like this is doing RMS. 10 volts peak to peak is 5 volts peak. 5 divided by square root of 2 is around 2.9. So looks like this is reading RMS voltage. So the symmetrical dynamic range is about 10 volts. And now let's crank it up and see the total dynamic range. So we're looking for clipping on the top and the bottom. And we're just starting to see some clipping on the bottom now. So now the peak to peak, the total dynamic range is 2, 4, 6, 8, 10, about 12 volts even. And 12 volts even, if we're going to measure that in RMS, is 4.17 volts RMS. So that is our total dynamic range. So what I'd like to do now is let's put in the bypass capacitor and repeat those measurements and see if they're the same. So the bypass capacitor is going to go across RE. It's going to go from emitter to ground. And let's put that on the bottom so that it's easy to take in and out. So the bypass capacitor is here across the bottom now, and we just need to run one jumper from the bottom bus up to the top bus. We need a jumper that's been stripped. So will that reach? Yes. We're just going to quickly strip this jumper and plug it in there. When I was younger, I did this with my teeth, and they got to be very crooked. But you couldn't beat the convenience. You carry your teeth with you everywhere you go. Okay, so let's plug in a jumper from the top ground bus to the bottom ground bus, and let's see. Okay, what we see is our output is now turned into what looks like a square wave because it has so much more amplification. Okay, and what we can see now is our peak-to-peak dynamic range now is we're on 5 volts per division. Let's move it down so it lines up with the marks. Our peak-to-peak dynamic range is now 5, 10, 15 volts. If we're going to measure it with the meter, it's around 6.56. And now let's turn down our gain, our input signal, to take this out of overdrive. You can see it's so bad it's even clipping the input wave. So now let's reduce our amplitude. And it's getting better, but you're going to notice a lot more waveform distortion. Now at this point I'm going to switch and trigger on channel 2 because this wave is getting too small for the scope to really grab it, and you can see it's starting to get noisy. So let's go back to triggering, source, channel 2. Okay, now it's holding nice and steady, and we can continue to reduce our amplitude. And we can see that we're down to 100 millivolts peak to peak. I wonder if this can get any smaller. Looks like it can. So let's turn these up. Okay. And we're on a triangle wave, but it looks like it's still pretty much undistorted. Now you can see how noisy and staticky this input signal is. So we're going to use a trick. We're going to put on the averaging feature. And the averaging feature will average out the noise, which is random, and give us a more steady signal. So let's move this up. And we can see that it cleaned it up nicely. It's a lot less noisy than it was before. And we can also see that we have this distortion. This high gain amplifier does give you this kind of distortion. We can continue to reduce the input signal. The scope does become rather sluggish when the averaging is turned on. But if we would like to measure a gain, let's go back to a sine wave, waveforms, and the sine, and it'll look a lot better. So there is still some distortion, but if we're going to measure the gain, our scope is turned up as high as it can go, 20 millivolts per division. It looks like we have an input signal of about 16, 17 millivolts, and we have an output of 2.3 about. So bypass, we now have a gain of 2.3 divided by about 17 millivolts, which is about 160, 170. So we can see that this is making a much higher gain bypassed than it did unbypassed. So, but still, it's a pretty nice looking signal. We have a nice round looking sine wave with no fuzz in it. And let's do the symmetrical dynamic range, the symmetrical dynamic range. We're just going to crank the input up until we see the first hint of clipping on the output. And we're going off the screen here, so let's continue to make that bigger. And we're not seeing clipping, but what we are seeing is some harmonic distortion. If you notice how this is getting a little sharp and this is getting a little round. This is the kind of distortion that does show up if you're listening to audio, for example. So technically it's still making the wave, but the wave is not as accurate a reproduction of the input as you'd like. And you can see it's just getting worse and worse. Okay.
You're also only changing 1 millivolt at a time.
Right. It's because the gain is so high. But it's pretty fair to say that we have some distortion up here, and where this first starts to come into play is right about there, and this is very subjective. This is very subjective. So at this point here, we have a total dynamic range on the output of, if we're on 5 volts per division, that's about 9.5 to 10 volts. And if you'd like a digital reading, it is 3.511 volts RMS. So we can count this as our symmetrical dynamic range. Okay, so all that's left now is to measure the input impedance and the output impedance. And again, I'd like to do them both. Input impedance with and without CE, output impedance with and without CE. So what we're going to do for that is we're expecting an input impedance of about 20 or 30K. And so for that, I got us a 100K pot, which should give us plenty of range. So what we'll do is we will unplug RS and put this pot in its place and use this to get the output signal cut in half. So let's reduce our input so we have a nice, clean, measurable output. So let's reduce our input. So their output is maybe, what, 4 divisions or so peak to peak? So right now our output is 4 divisions peak to peak. So from there, 1, 2, 3, 4. So when we set the pot, we're now going to bring it down to 2 divisions peak to peak. That will be our value. And for measuring that, why don't we just use this handy dandy digital multimeter? This is a BK Precision Test Bench 388B multimeter number 0714. So we'll use this to measure the pot so we don't have to reconfigure our voltmeter here. And some probes just magically appeared. So right now we have our circuit humming along, and we're going to, let's find a better way to apply our input voltage here. I'm going to clip this onto the capacitor. And then because we're pulling out this 1K resistor, technically we could probably just leave it in place. But let's bar this jumper temporarily, and we're going to use this to apply V in. And we'll just have to remind B to put it back when we're done. Okay. So hopefully the signal will still be there, which it is. Interesting, we saw some oscillations in there when the input was floating. Okay, so now we are free to unplug RS, the 1K resistor, and we're going to plug in the pot using the center lead and one of the side leads. The center lead, let's center the pot before we plug it in. Okay, and put that back. And what we're going to do is turn the pot to 0. Make sure we still have our 8 volts coming in there. It's actually a little bit more now because the RS, the 1K, is gone. Let's crank that down until we get to about 8 volts. Okay. Now we're going to bring the pot up in value until that output, so that signal gets cut in half. We do have some oscillations in there. Not sure why that is.
You want to turn off averaging?
I think it's better to leave it on and get the waveforms clean. So right now we have an output is 2 volts peak to peak. We can slide this down. And it goes from there, 2 divisions there. So the signal's been cut in half. So now let's take the pot out and measure between the black and the yellow. That is our Rin bypassed. So we're going to put this on ohms, 40K scale. And we get an Rin of about 4.7K. So your measured value of Rin is about 4.7K. And then the theoretical value is going to be R1 parallel R2 parallel R pi. And hopefully that's going to be in the same ballpark. Okay, so now let's go back and do this again unbypassed. And also we should take out R2 and measure R2 before we stop, so that we have our value for R2 for your calculations. So let's see if we can get that to plug in there. There we go. All right. So now let us unplug CE. We're getting our unbypassed signal. And again, we want to set this until we get to 2 volts, 2 divisions. And it looks like it's we have to crank up the input signal, don't we? All right, so it's working, but the input signal is too weak. So now let's go to parameters, amplitude, and we have to make the input signal way bigger now in order for get this thing to work. Okay, so I'm going to set the pot back to 0. That's more like it. And we're going to set, let's see, go for 4 divisions peak to peak. Right now, that's 4 divisions, 1, 2, 3, 4. Okay, and that now we're going to tweak the pot until that drops down to 2 divisions peak to peak. Much better. Right about there. 2 divisions peak to peak. So now the resistance of the pot is equal to the input resistance of the amplifier. And what's nice about this, we're doing this measuring V out and not V in, so that the meter doesn't disturb the input side. And the pot for this one is around 7.97 K. That's the input impedance unbypassed. Okay. So now we can go ahead and replace our 1K resistor back into place for RS. We're done on that side. Okay. And then now we can do the output side. So what we'll do is this 10K resistor is a convenience for us in that it gives us a place to hook the probe. So I'm just going to temporarily unplug it. Okay, and just plug it in an empty space. And we're going to use we now have a 10K pot to do that. And the reason I chose 10K is because 10K is about the expected output impedance. I guess a 20K pot would have been ideal. We'd like the middle of the pot to be where we expect it to be, where we expect the output impedance to be. So there, and then the center lead, the black lead, goes to ground, there. Okay, and I did forget to center this pot. Luckily, there's RC in series with it. It's not going to hurt it. So we're going to unplug the pot, set our signal for about 4 volts, 4 divisions peak to peak. About there. 4 divisions peak to peak. Let's slide it down just to here to get good alignment. Okay. And now what we can do is plug in the pot and try to set it for 2 divisions peak to peak. So we're going to connect that to the ground bus and go for about 2 divisions peak to peak, which is about there. Okay. So 2 divisions peak to peak, take it out, measure it across the black and orange leads. Black and orange. We get about 9.8 K. Remember, we're expecting about 10 K parallel with little RO, and we're getting about 9.8 K. Okay, so let's put this back in, and let's just see if it makes any difference having it bypassed. So we're going to reinstate our potentiometer where it was before. And with the bypassing, I have a sneaking suspicion that installing the emitter capacitor is not going to change very much. But there's one way to find out. Okay, let's crank our input signal way down. Okay, so there we have about 4, let's go a little bit bigger. We have about 4 divisions peak to peak. That's so. And, oops, I guess, let's set this for 4 divisions peak to peak. This is the pot unplugged. This is unloaded. That's 4 divisions peak to peak, and we'll see if this drops it down to 2 divisions peak to peak. If it does, it means the output impedance is pretty much the same as it was before. It's just a hair above. So let's tweak that until we get to about like that. Okay, so right now our pot is dividing our input signal half. So bypass, our output impedance is going to be, the envelope please, 8.73K. So it's very similar to what it was bypassed versus unbypassed. Output impedance really does not change very much. So the only thing we really have left to measure, let's take out the pot for R2 and measure that. That way you can plug it into your calculations. But we can see that the amplifier gives us a lot of gain of close to 200, which is really not bad at all. So all that's left now is to take out R2 and measure it. So I'm going to shut off the power supply. We're done with that. We can disconnect this and pull out this pot for R2 and measure that and see what we had for R2. And you'll need this for your calculations. R2 has a measured value of 8.77K, 8.78K. So that would explain why our input impedance was low, is because R2 was so low as well. So about 8.7K for R2. So with that, you should have all the numbers you need to do your theoretical values. Remember to present your data in the tabular form like I suggested, and we'll all live happily ever after. Okay, that's it.